Hello everyone, and welcome to Dark Alice tutorial. In today's session, we are going to perform a deep dive into the XGENIA slot template to understand its full capabilities. We will begin by dissecting the overall architecture of the template. From there, we'll move into asset management, tweak the core backend functions, and finally, we'll break down the underlying mathematics that drive the slot system. So, let's get started. To begin, we need to initialize our environment. We can pull a pre-configured project directly from the XGENIA template library. Simply navigate to the project menu and select New Project. Among the available options, we'll be selecting the Dark Alice template. Once selected, the system will load all the necessary dependencies and assets into the workspace. Now that the project is open, let's look at the workspace. You can see the canvas in the center representing our viewport. On the left, we have our hierarchy, where we can manage the various layers and components that make up the game interface. It's important to understand the structure here. We have distinct containers for the reals, the background layers, and the interactive UI elements. Each node in this hierarchy corresponds to a specific object on the canvas. The green node is affecting the UI of the template. So you can see the UI setting on the left side panel, such as margin, alignment, layout, and more. While the blue node is the function. Try to double-click it. You will see the function here. Let's try on any other node. By examining these functions, we gain insight into how the backend logic communicates with the front-end UI. This modular approach allows us to tweak specific behaviors without breaking the entire system. Next, let's look at how we handle assets. By heading into the project settings and opening the project folder, we can access the underlying file structure of the application from the local directory. Inside the project directory, we see the root assets. The UI folder contains all the core interface elements. This is the directory we'll be working in when we want to replace default graphics with our own custom designs. We've got some assets here. So let's open the asset project. Copy everything, make sure the namings are all the same, and then replace it. Do the same with the icons. And the background too. All right, now that we've updated our assets, we need to refresh the environment to see those changes take effect. We can either use the Ctrl+R shortcut or simply click the reload button in the interface here. As we can see, the assets have been successfully updated in the project files. However, we still need to perform some manual tweaking on the background elements to ensure everything aligns with our new design. Let's head over to the background video animation section. We need to clear out the existing video nodes. We'll simply drag to select all of them and hit delete to clean up our workspace. Now we'll right-click in the empty space, navigate to the node options, and select the image node. This will allow us to map a static graphic to our background instead of a video file. We can now see our background PNG in the asset list. We'll select that file, and as you can see, the background has instantly updated in the viewport. It's looking much better already. Let's trigger a test run to see how it looks in real time. It appears we're still seeing some of the older assets in certain sections. This usually means there are hard-coded paths we haven't updated yet. Specifically, we have some custom icons located at certain indices that are still referencing the old template files. We need to locate these specific icon animation nodes and swap them out manually. Let's use the search bar and browse for Special Icon. We'll go into the Special Icon Animation section. This is contained within a group node. By double-clicking here, we can see the Special Icon Animations. Currently, these are utilizing the WebM format for high-quality transparency. We need to change the source format to MP4, as that is the format we have prepared in our new asset library. We'll update the extension and point it to the correct file. To keep our project clean and avoid any pathing conflicts, we'll delete the older icon assets from this directory. Once that's done, we'll give it a quick refresh to finalize the changes. Let's run for testing. All right, it's running perfectly for now. Now, let's tweak some functions from our nodes. Start from this spin function node. Here, we can edit the scratch blur and adjust the scale of the blur for each individual icon. Additionally, we have control over acceleration inputs, including the max speed settings. We also have settings for the blur threshold, normal breaking, quick breaking, and real offsets. While we can edit these inputs directly from the left side panel, the configuration options there are not yet fully complete. To perform more advanced editing, we can open the core functions directly. For this demonstration, let's set the max speed to 10 and the acceleration to 0.5. Next, we will set the scratch factor to 1 and the blur threshold to 5. We also want the real delay to be faster, so we will adjust that here. Let's test these changes. Cool, it's running well for now. Now that we have finished tweaking the core functions, we can move on to the slot math fundamentals. The entire math engine is wrapped within the slot engine parent component. This ensures that all mathematical logic is contained within a single parent project for better organization. Within this structure, we can see how the logic flows. Everything related to the game's math and outcomes is handled here. To ensure security and fairness, the spin results are not calculated locally. Instead, they are wrapped in cloud functions. When a spin is triggered, it sends a request to the cloud function. We can see the signal triggering through every node here and proceeding to the final result. Once the process is complete, we can see the resulting total winnings. By double-clicking the spin result function, we are redirected to the specific cloud function logic in the map. This container handles the real strip generation, spin calculations, winnings, and final results. The logic flow follows a signal triggered when the spin button is pressed, moving from left to right through the nodes to calculate the total winnings. Most of these are handled via cloud functions. Double-clicking a node like spin result will redirect us to the corresponding cloud-based logic. Our math logic is split. Some processes run on cloud, while others, like the weighted reals, run locally. This hybrid approach gives us flexibility. We can keep nodes local for speed or deploy them as cloud functions for better security and data management. That concludes today's tutorial. We have explored the template structure, customized assets, tweaked core functions, and broken down the math engine. Thanks for watching. Get XGENIA for free today at xgenia.ai and start building smarter and faster than ever.